Graph Convolutional Networks, GCNs, Part 3, Tasks on Graphs. Stay tuned for more tutorials at LearnAI_CV. In this video you will learn tasks on graphs including node classification, node regression, link prediction, graph classification, and graph generation. As you saw in the previous videos, there are different types of graphs, and they are used in different fields. Graphs are powerful tools for representing heterogeneous data. Now, you will learn what tasks we can perform on graphs. We can store information in nodes, edges, and the entire graph. So, there are three general types of prediction tasks on graphs: graph-level tasks, node-level tasks, and edge-level tasks. In a graph-level task, we predict a single property for a whole graph. For a node-level task, we predict some property for each node in a graph. For an edge-level task, we want to predict the property or presence of edges in a graph. A fundamental task on graphs is node classification, which tries to associate each node with a predefined label. For example, in a citation network, the aim is to predict the field of each paper. In a protein complex, the goal is to predict the function of each protein. In the World Wide Web, we are interested in classifying web pages to semantic categories. The node regression task is very similar to the node classification task. The difference is that the nodes associate with continuous values or vectors. An example of the node regression application is traffic control. We can model the roads in a city by a graph in which the roads are the edges of the graph and the number of existing vehicles in each road is considered as the edge weight. Prediction of the traffic flow in different places can be modeled as a regression problem. Link prediction is defined as forecasting the existence of a connection between two entities in a graph. Link prediction has different names such as matrix completion or graph completion. The link prediction task has applications in recommender systems such as recommending a friend in social networks and suggesting a product in e-commerce companies. Drug response, drug-target interaction, and polypharmacy side effect prediction are other important applications of link prediction. The goal of graph classification task is to categorize a graph to a predefined label. A promising application area of graph classification is pharmaceutical drug research. Researchers use GCNs to classify different molecules with the intention of discovering new candidates for antibiotics. Text classification and image classification are other examples of graph classification task. The research of graph generation is about discovering probabilistic models over graphs. Drug discovery is one of the applications of graph generation where researchers attempt to create molecules with specific properties. Another application of graph generation is scene graph generation that refers to the task of mapping the objects in an image to a graph in which the semantic relationships between different objects are modeled. Stay tuned for more tutorials at LearnAI_CV. Graph Convolutional Networks, GCNs, Part 4, Why GCNs? Stay tuned for more tutorials at LearnAI_CV. In this video you will learn: why do we represent real-world data as graphs? Why do we should pay attention to deep learning on graphs? What are the challenges for deep learning on graphs? Why do we represent real-world data as graphs? The nature of the data in real-world is in the form of graphs. If we represent it in the form of tabular structure, a huge amount of rich information will be missed. Graphs can model the heterogeneous and complex data. What makes graphs different from other types of data is the relationships between different objects. Nodes on graphs are inherently connected, which suggests that nodes are not independent. Graph is a comprehensive and flexible tool for representing this dependence. Graph is a universal tool for representing data, such that other data types can convert to graph. A huge number of real-world problems can be addressed as a small set of computational tasks on graphs. Data from real-world applications have very diverse forms, from sequence and time series to matrix and tensor. Other types of data can be transformed into the form of graphs. We typically think of images as rectangular grids with image channels, representing them as arrays. Another way to think of images is as graphs with regular structure, where each pixel represents a node and is connected via an edge to adjacent pixels. Each non-border pixel has exactly 8 neighbors, and the information stored at each node is a three-dimensional vector representing the RGB value of the pixel. We can digitize text by associating indices to each character, word, or token, and representing text as a sequence of these indices. This creates a simple directed graph, where each character or index is a node and is connected via an edge to the node that follows it. Why do we should pay attention to deep learning on graphs? We need some tools to analyze data in the format of graphs and make predictions in applications involved graphs. One idea is to look at tools that have worked well in other format of data. Deep learning has been proven to be powerful in representation learning, which has greatly advanced various domains such as computer vision, speech recognition, and natural language processing. Therefore, bridging deep learning with graphs presents unprecedented opportunities. In past 2 decades, deep learning methods have achieved impressive successes in Euclidean data such as data in computer vision and speech recognition fields. What is Euclidean data? Euclidean data has a grid-like structure. Euclidean data is data which is sensibly modeled as being plotted in n-dimensional linear space, for example image files where the x and y coordinates refer to the location of each pixel, and the z coordinate refers to its color. A gray image is Euclidean data. It is represented as a two-dimensional matrix. A colorful image is Euclidean data. It is represented as a three-dimensional tensor. And speech is Euclidean data. It is represented as a one-dimensional vector. Here we show how a convolutional neural network works on a canal of image. The filter slides over the image, starting at the top left corner and moving left to right, then down to the next row, and so on. Then, it performs element-wise multiplication with the part of the image it's currently on. The filter sums up all the results into a single output pixel. This process is called convolution. The result of the convolution is a feature map that highlights specific patterns or characteristics in the image. What are the challenges for deep learning on graphs? Deep learning on graphs faces immense challenges. First, traditional deep learning has been designed for regular data such as images and sequences where the size is fixed, whereas graphs can have varied sizes, and nodes in a graph are unordered. Second, the structural information for regular data is simple, whereas that for graphs is complicated, especially given that there are various types of complex graphs, and nodes and edges can associate with rich side information, thus traditional deep learning is not sufficient to capture such rich information. Embracing the unprecedented opportunities as well as the immense challenges, a new research field has been cultivated, GCNs. Stay tuned for more tutorials at LearnAI_CV.